Binary search is something that you might have learned in your initial programming days. But you might be surprised to know that it involves some of the most efficient algorithms, and it is also used in a lot of production workloads almost every day. So, in this particular video, we are gonna explore more about this pattern. Hello friends, welcome back to my channel. When you think about binary search, what is the first thing that comes to your mind? It is not simply looking through a sorted array and finding an element. It has some of the most practical use cases. For example, when I take a book, let us say I have to search for the page number 78. My general idea to find that page will be, I will look at the middle page, approximately middle, and then look at where I landed. I landed on 156. So I know for sure that the page 78 that I'm trying to search will be in the first half. I can immediately discard the remaining half of the search space. So what is this doing? At every iteration, you reduce your search space by half. And it may feel that it is very small. But when you do it for a very large data set, the order of log and time complexity actually becomes very, very fast. And that is why this divide and conquer technique can help you to solve a lot of problems. So let us start off with something very, very basic. How do you actually apply the binary search? So let us say I am given a sorted array and you have to search for a number. You can see that I have this sorted array with me. It is sorted in an ascending order and I have to search for the number 3. A linear search would mean that you start from the beginning and then keep on traversing the array until and unless you find your number. But with a binary search, you can take advantage of the fact that your array is already sorted. The basic idea for binary search is that I will have a left pointer and I will have a right pointer. Now, based upon these two indexes, I can look at my middle element. I land at my middle element and that is 4. Now, how am I taking advantage of this? I have to search for the element 3. It is very sure that all of the elements after this particular element will be greater. So what does that mean? My result, it won't exist over here. I can straight away discard this particular array. But I am now left with an even smaller array. So what do I do next? I will update my right pointer and I am gonna move it at this particular location. Once again, you take the left and right, find out the middle element and then again compare it with the number you have to search. This time your number is higher. So what had we done in the first iteration? In the first iteration, we got rid of some part of the array. In the second iteration, I can get rid of some more additional array. So now what will happen is my sample space gets even more smaller. You see how in just 2 iterations, I am now looking at such a small space. That is the power of binary search, and that is how you can quickly look up elements in a sorted array. So that is the very basic idea upon which this pattern is built. We are looking at sorted numbers, sorted sequences, and then we divide and conquer until we get the solution. Similarly, you can now extend this pattern. For example, take a look at this particular question, search insert position. What you have to do is, you are given a certain array and you have to tell me where can I insert the number 15 such that this array remains sorted. How would you approach it with a linear method? You will start to navigate your entire array and you will keep on going ahead until you reach a number that is bigger than 15. It simply means that you will have to insert 15 at this particular position. So you return this position as your answer. This is the method, right? How can binary search help you? Once again, what I'm going to do is I will take up 2 pointers, left and right. What is the middle element? The middle element is 4. So in just one instant, I know that this number that I'm inserting, it will never be inserted at the left of this middle element. So I can straight away discard this entire space, right? I am only left with this smaller space now. So what I will do is I will update my left pointer over here. What do you do in the next iteration? Again, you will apply the binary search and you will land at a middle element. So what do we know now? We know that I will not find my result even here. So what am I doing over here? At each step, I am reducing my sample space. And now I can simply say that, okay, after this particular position, I will want to insert my element. Because I have removed this half of the array also, my pointers have now moved. Look at left and right. Right is at 11 and I know that all of these elements are greater than 15. So where will it go? It will definitely go between 11 and the remaining elements. So that is your answer. Once again, binary search helps you to quickly get to the solution. You might have noticed that in both these examples, my array was sorted in an ascending order from beginning all the way towards the end. There are also different questions possible where an array might be sorted but it is rotated also. What does that mean? For example, I have this particular problem. You have to search for a number in a rotated sorted array. So look at this particular array. It is sorted but rotated also. Because if you start from -12, all of these numbers are in an ascending order and now it is rotated to find other numbers in an ascending order also, 11 and 20. So the array is sorted. Can you leverage the binary search? Yes, but you might want to have some additional checks also. For example, if you try to apply binary search in the most conventional way, you have a left pointer and a right pointer. What will happen? You get the middle element. Let us say you will have your mid somewhere over here, correct? Now, as soon as you find the mid, notice what will happen. One half of the array will always be sorted and the other half of the array will again be a rotated sorted array. And how can you check that? Just look at the first element and the last element. If the first element is smaller than the last element, it means that this array is completely sorted. However, if the first element is larger than the last element, it means that this array is again a rotated sorted array. So you can find a problem within a subproblem, right? If you also look back at the original problem, the first element is greater than the last element. That is why this array was rotated and sorted. So what does this land up to? I can say that I will need to find my number within this particular array because I have to look for 3 and 3 will lie somewhere between 1 and 8. So what can I do? Immediately I can discard this particular array and I can safely apply my binary search technique as usual in this part of the array. That's it. Binary search can help me again. But what happened if I would be looking for a number, let us say 20 over here. I have determined that, okay, this part of the array is sorted. But will you be able to find a 20 in here? No, because the largest number is 8 itself. So what will happen now? You are gonna remove this entire search space and you are left with this particular array. You will again take your left pointer and the right pointer. And now, once again, you will try to partition your array. As soon as you partition it, once again, you will be left with one half of the array that is sorted and one half of the array that might be rotated and sorted. So once again, it is a repeated pattern and you can use the same technique to search for this number in the remaining halves as well. So once again, applying binary search 2 times helped you just with a little bit of slight logic. Now when you think about it, there is a lot of things that go behind a binary search framework. The binary search algorithm is just kind of a tip of the iceberg. You are all knowing the common algorithm. Take a left pointer, take a right pointer, divide by 2, get the mid position, and then proceed ahead. That is just the algorithm. But underneath, a lot of other things are happening. At each instance, you just halve the search space. That will greatly help you with your very huge data sets. And that is why you have logarithmic time complexity. That is the best time complexity you can practically have. Along with it, you also have adaptive problem solving because based upon certain conditions, you can still apply the binary search technique. And we are gonna see more of this in the upcoming problems that I have to discuss with you. The last part is really very interesting, searching for answers. This is the time when we apply binary search in answers itself. But let us wait before getting to it. The next type of problem that I want to discuss is finding the first and the last position in a certain array. Over here, if you notice, I have this sorted array available. And it straight away means you can try to apply the binary search algorithm. You see that all of this array is sorted, but this number 3 is repeated several times. And what do you have to do? For this given particular number, you need to tell me the first position and the last position. So when you're actually searching, are you searching for the number 3? No, you are searching for the first position of number 3. Just look at all of these 3s. They may look the same, but this first 3 is very different from all of these 3s. And this last 3 is again very different. How? For the first 3, the left element is smaller and the right element is equal to 3. And for the last 3, the left element is equal and the right element is greater. So technically, we need to apply the binary search algorithm 2 times. For the first time, we will try to find a 3 which has the left element smaller and the right element as equal. And then we will again apply the binary search technique to find where the left element is equal and the right element is greater. So let us say you want to find the leftmost occurrence first. You are gonna apply your binary search technique. You take up 2 pointers and then you land at the middle element. You see that, okay, this is a 3. But is this the 3 you want? No, you want a 3 where the left element is smaller but the right element is equal. This is not your scenario, but it is a 3. So you know that I will find my leftmost element somewhere over here. So what can I do? I can simply get rid of this half of the array. I reduced my search space. And now what will I do? I will take up my right pointer and I'm going to move it over here. Once again, apply the binary search technique and you will land here. Ultimately, what is going to happen is you will land at this particular 3 where your condition is satisfied. You found out the leftmost position. Similarly, you will apply the same technique to find out the rightmost position and you are going to land at this particular 3. So once again, applying binary search by adapting. You adapted to a certain condition and then you found out your answer. Similarly, there is one more problem statement also. Finding the peak index in a mountain array. Now, a mountain array is just a made up word. Just look at this particular array. If you notice, this array has elements that keep on increasing all the way up to 8 and then they start to decrease again. So technically, what are you looking over here? You have to find a peak in a mountain array. And this is a mountain because it increases and then decreases. Where is the peak? The peak is this particular element. You have to return in this location. But you are not searching for 8. Neither you are searching for any specific element. What are you searching for? You are searching for an element which is greater than the left element and which is greater than the right element. And this is true only for the peak element. If you notice, for all the other elements, this is the scenario. You will only have one element which is greater than its left and right as well. So how do you adapt for binary search? Once again, you will take 2 pointers. And now, are you looking for something? Yes, but it is not the element. You will sort and you will try to look at the middle position. You found out this middle position, but over here, this particular number is not the peak because the left number and the right number, they are smaller and larger respectively. So you know that, hey, my peak does not exist over here. So either your peak is going to exist in this part or your peak is going to exist in this part. You can apply the same technique recursively on both these parts and ultimately you will find a specific number which is greater than both the left element and the right element. Once again, binary search helps you to narrow down the entire space and you adapted your binary search algorithm according to the condition that you have to solve for. From all these examples, what do you understand about binary search? It is not just looking at a sorted array. Binary search is an algorithm or a pattern which you can adapt and solve and apply at multiple different places. And we are certainly going to see more examples on it. But you might be getting a general idea. For example, if you have a monotonic search space, that means you know a certain pattern. You know things are going to increase and things are going to decrease. So there is a certain pattern you can follow. That is a straight away giveaway that you can apply the binary search technique over here. Similarly, try to think how we were adapting to the situation. It was not just that we looked at a specific number. You are actually trying to determine a Boolean condition. Based upon a certain condition, if it is true or false, you can decide to reject one half of the array and then only search in a defined space. And that gives me the next point. Your search space is defined. If you are not sure where the answer can be, then binary search will never help you. Binary search is always good for spaces which are monotonic in nature and you know the limits as well. Because only then you will be able to have a left pointer and a right pointer, right? And then you can narrow down. And this brings me to a very interesting concept. You do not have to apply the binary search just on the given input set. I know that this is the first thought that comes to our mind. As soon as we see a problem, we try to analyze the input and we will try to apply the binary search technique on it. And sometimes you may realize, hey, I can't even apply binary search over here. But that is not always true. Sometimes you can also apply the binary search on your answer space as well. And that is why I mentioned your search space should be defined. You must know that, okay, I can have my maximum answers between 0 and this particular limit. So let us take up an example on this particular scenario. There is a particular question on LeetCode, capacity to ship packages within D days. The idea over here is very, very simple. You have packages that arrive in this following order, and these are the weights of these packages. So first package is 3 kg, then 2 kg, then 2 kg, 4, 1, and then again 4 kg. What you have to do is, you have to ship all of these packages within 3 days. On a single day, you can have one boat that can carry all your packages. But that boat will have some capacity. So you need to minimize the weight required for the boat. So try to think like this. If I have a boat that has an infinite capacity, just on day 1, I can load all of these packages and send it away, right? I was able to ship all the packages in just one day. But that is not the answer. I need to find the minimum weight capacity required for the boat. And I also have to use up all of my 3 days. That is also a very big hint. So what am I defining over here? I am defining a kind of search space. I know that I cannot have a boat with a capacity 0, because if it is 0, I cannot ship any packages. Can I have a capacity of 1? Yes, I may have a capacity of 1, but I do not know yet how many packages can I ship. And what is the maximum capacity? We just said that if a boat has infinite capacity, you can ship all the packages. But do you really need an infinite capacity? No. If you have a capacity of the total of all of these weights, that is equal to 16. So if I have a capacity of 16, then also I will ship all of my packages in just one day. So what did I just do over here? I made my search space finite. I know that my answer will lie somewhere between 1 to 16. That's it. It is giving me a hint of binary search. And how do I do it? I know that my answer will be between 1 and 16. So these are intentionally my 2 pointers. Find the middle element. The middle element will be 8. So what you can do is, you can try to keep the weight of the boat as 8. And now try to ship packages. When the boat was 8, on day 1, you can send 3 plus 2 plus 2. That is 7. It is within the limit. I can send the packages. On the next day, what can I send? I can send 4 plus of 1. That is 5. That is good too. And on day 3, I can send the 4 remaining package. So in 3 days, I was able to ship all of the packages. So 8 does look like a good candidate. But is it the answer? I am not sure yet. But definitely we did one thing. Do you remember how my search space was between 1 all the way up to 16? With binary search, what I did is I found out the middle element, that is 8. I knew that with 16, I will be able to ship all of my packages. I know that with 8, I will be able to ship all of my packages. It clearly means that any number between 8 to 16, I will be able to ship all of the packages. So it is the time for elimination. I know that the minimum weight it will never be between this range. So once again, what did I get? I am getting a left pointer as 1 and a right pointer as 8. So once again, what will you do? You will try to find a number between over here. Let us say you found the number 4. So what you're going to do is, you will try to determine if you can ship all of the packages with a weight of 4. With a weight of 4, on the first day you can only ship 3. On the second day you can ship 2 plus 2. On the third day you can only ship 4. So you still have these packages remaining. That means 4 does not work for you. So I can again eliminate all of these options as well. So what I'm doing, I'm applying binary search on my answer space. Notice what I did over here. My initial search space was between 1 to infinite. I reduced that to 16. Then again I reduced that to 8. I eliminated this. Now I'm reducing it between 4 to 8. So eventually you will land at the perfect answer, and that is the minimum weight capacity required for your boat. And that is how you are applying binary search on your answer. Let us look at one more example. And now I think you will be able to solve it on your own. You might have seen another similar problem, and that is Koko eating bananas. Koko is a monkey and it has to eat bananas from these piles. First pile has 30 bananas, then 11, then 23, then 4, and then 20. Koko also has some hours available. He has to eat all of these bananas in these 9 hours available to you. And now you have to tell me what is the minimum eating speed that Koko must have so he can finish all of these bananas. The only catch with this problem is that, let us say Koko is eating at a speed of 8 bananas per hour. So for the first pile, he's gonna eat 8, then 8, and then 8. He has eaten 24 bananas. So 6 are still remaining. In the next hour, he has to eat 6 and then he has to stop. He cannot eat 2 bananas from this pile. That's it. This is the only catch you have to be careful about. So how do you find out the minimum eating speed of Koko? You might have already guessed it. It is very similar to the previous problem, right? Try to think like this. If Koko was eating at an infinite speed, what will happen? In the first hour, he eats first pile, then second pile, then third, then fourth, and then fifth. So in just 5 hours, he was able to eat all the bananas. But he has 9 hours available. So you need to use that. But at the same time, if you notice, he does not need an infinite eating speed. If he is able to eat at the speed of the maximum bananas in a pile, then also he can achieve it. So if instead of eating at infinite speed, Koko eats at 30 bananas per hour, then once again, in every hour, he will eat all the piles and he will be done. So up till now, what have we done? We reduced our search space from 1 all the way up to 30. You definitely know the next steps, right? I will have my left pointer at 1 and right pointer at 30. So where is 15? I get 15 over here. So now what I will try is, I will try to eat at 15 bananas per hour. The first pile is going to take me 2 hours. The second pile is going to take me 1 hour. Third pile takes 2 hours. Fourth pile takes 1 hour. And fifth pile again takes up 2 hours. So how many hours did it take? 8. In 8 hours, Koko was able to eat all of the bananas. That means I'm still left with 1 hour. But also, I know that for any value that is greater than 15, I am not utilizing all of the 9 hours available. So what I'm doing over here, I am reducing this search space. I know that my answer will lie somewhere between 1 and 15. Once again, apply the binary search. Take the right pointer at 15 and now find a midpoint. Using this midpoint, try to eat all the piles and see how many hours do you take. Based upon this, you will find your answer, and once again, binary search helped you in your answer space rather than the input set. These are all the reasons which make binary search super interesting. You are not only applying it at your input space, but you can also apply it at your answer space as well. So whenever you are approaching a problem, look for all of these pattern recognition cues. They will help you to understand if you can apply the binary search technique or not. For example, space properties. Your space is sorted, monotonic, bounded. You have an increasing or a decreasing function. Sorting simply means try the binary search. You are picking up an option based upon a Boolean condition. You are able to discard some of the spaces. You are want to finding out the minimum value. You're trying to achieve a certain target, some kind of a feasibility. This is a very good indication that you have to search in your answer space rather than looking in your input space. So try to look for all of these cues, and I truly believe this pattern is gonna do wonders for you. Just tell me all in the comment section below, where else have you been able to apply this binary search pattern? This will become a very good collection of all such problems, and it will help you also when you come back to this video for a review, and you will have all these questions ready for you. Do let me know in the comment section below, and I would be happy to discuss everything. As a reminder, if you found this video helpful, please do consider subscribing to my channel and share this video with your friends. This really keeps me motivated and I can make more such videos. Remember, you can now schedule a one-to-one session with me and we can solve any sort of doubts or questions that you might have. Also, a huge shout out to all of the members who support my channel. You guys really keep me going. Because as a member, you do get priority reply to your comments and early access to new videos as well. Stay tuned for my upcoming video. Until then, see ya.